We will continue looking at the inflow models for rotor in hover. Thus far, we have looked at two particular models. The first one is based on a very simple actuator disk. In that model, the inflow was assumed to be completely uniform. So we got some analytical expressions, for example, lambda I, which is a non-dimensional inflow ratio in hover, was simply the square root of Ct, which is the thrust coefficient, divided by 2. Ct over 2 is inside the square root. We also looked at combining the blade element theory and momentum theory, and we came up with a combined blade element momentum theory model. We also talked about how to correct it for tip loss effects. Tip loss effects account for the fact that as you approach the blade tip, the lift is going to zero. So a factor called F was introduced. This factor F is a function of radius, but it's also a function of lambda I, where lambda I is the induced inflow. Because F depends on lambda I, and lambda I depends on F, some form of an iterative process is needed. You initially start with F equal to 1, then solve for lambda I, and put that lambda I into the calculation for F and keep iterating. So at each radial location, you'll get one value of F, which is the tip loss factor. You'll smoothly go from 1 all the way to 0 right at the blade tip. Now we are going to look at more advanced theories for vortex theory. These require digital computers, and we are going to briefly look at these methods. It's a very, very short presentation that we will look through. So let me go to the full screen. So this is also called the hover performance prediction methods. The theory that we are going to use is called the vortex theory, because these are primarily based on the tip vortex and inboard vortex structures and how they influence the inflow. So this is an extension of Prandtl's lifting line theory in aerodynamics. So in the classical aerodynamics, Prandtl said the airplane wing can be thought of as a line of vortices that produces lift using a theorem called the Kutta-Joukowski theorem. And so because the strength of that vortex is changing from point to point to point, Helmholtz theory says the circulation or the vortex strength of a vortex tube should be a constant. So if things are changing from one span location to the other, then you must be losing circulation or losing vorticity. So you are forming what you call trailing vortices. The largest and strongest trailing vortex is the tip vortex, which we see when the airplane is flying above board. So our theory is an extension of Prandtl's lifting line theory, going from a fixed wing to a helicopter rotor in hover. So we are going to refer to some theorems and some physics. If you have not seen it before, don't worry. We are going to cover it as much as possible in this lecture. And it also requires some empiricism, some algebraic quantities, curve fits from experimental data. The earliest model of a vortex theory or a tip vortex structure was developed by Professor Robin Gray, who was an associate chair in aerospace engineering, and he retired around 1996, right around the Olympics. He received his PhD at Princeton, and his PhD dissertation was what he called a prescribed wake model. At the time, he was able to model only small-scale rotors, and he continued to work on it even at Georgia Tech when he came back to Georgia Tech. But he was able to model only a very small-scale models, rotors. When I say small-scale, I mean the radius is of the order of a few feet. And sometimes one-bladed or two-bladed rotors. How did he look at this wake structure? He would introduce smoke particles into the tip vortex. Then the smoke will follow the tip vortex structure, so it will follow the flow field. Then you'll take a camera pictures, still shots or video shots. Then from the video shot, he will try to see what is happening to the tip vortex, how is it behaving, what is this geometry looking like, and that's what he did. Almost 18, 20 years later, Jack Landgrebe at United Technologies and one of his very able assistants, Alan Egolf, extended Robin Gray's model from small-scale rotors to large-scale rotors. That means we are talking about now instead of 2 or 3 feet diameter rotors to 60 feet diameter, 50 feet diameter large-scale rotors. Not just 1 or 2 blades, but also 3 blade, 4 blade, as many blades as you like. So he took a lot of data using a technique similar to Dr. Gray's model, except because this was done 20 years later, not in 1950s. Visualization techniques, smoke visualization techniques, computer animations, videos, digitization, laser velocimetry, all kind of new experimental techniques were available. So he was able to extend it. From 1970 until early 1980s, late 1980s, this was the way the tip vortex structure was modeled in many helicopters. After 80s, there were other techniques developed, free wake models. They were also started in 1970s, but they matured with improved computers in the 1980s. But also computational fluid dynamics models became available. Towards the end of this course, as time allows, we will look at how to model helicopter rotors in hover using computational fluid dynamics techniques. So this theory has got some drawbacks. It removes some of the drawbacks from our combined blade element momentum theory, which you saw in the earlier lectures. Especially at high thrust setting, the induced velocity from the combined blade element theory is very poorly predicted, particularly near the tip. Therefore, the tip is producing more thrust, and the power consumption is also different. Remember that velocity goes as omega r. Therefore, the dynamic pressure varies as omega r squared. Torque is omega r squared times r, therefore it varies as r cubed. So near the tip, many important things are happening. So these things were not properly captured by the combined blade element momentum theory. Also, it turns out that the tip vortex is contracting. That means it's going inboard. So it's like a spinning vortex. So it produces the inflow on one part of the rotor disc, inboard, but sometimes it will produce an upwash, which is the flow going from the bottom of the rotor disc towards the rotor disc and above in the outboard region of this vortex. If you think of the vortex as a spinning vortex, on one side the flow is going down, other side the flow is going up. So combined blade element momentum theory was not able to capture this effect due to the contraction. So this changes again the tip loading. Loading means the lift distribution, tip induced velocity distribution, therefore the induced power consumption. And of course the angle of attack changes, therefore even the CD and the profile power would be affected. So a better model than the combined blade element momentum theory model is needed. So I mentioned some theories, theorems called Kutta-Joukowski theorem. So let's talk about briefly what is a Kutta-Joukowski theorem. Kutta-Joukowski theorem says, first you compute all the circulation surrounding the airfoil. Remember, the airfoil has got a vorticity in the boundary layer on the upper side and also the lower side. On the upper side of the airfoil, all the vorticity is spinning clockwise, primarily. On the lower surface, all these vortices are spinning in the counterclockwise direction. Okay. So if you use a Stokes theorem, which is the vorticity times the area, you'll get a circulation. So this circulation would be, you could also compute a circulation using a line integral of velocity dot distance over a contour that is surrounding the airfoil. So this circulation is called gamma. So this circulation would be in the clockwise direction. Kutta-Joukowski theorem says that the vertical lift, delta T, or the vertical thrust in the case of a helicopter rotor, is density times forward speed of the blade section, which is omega r, times the circulation gamma. And it also says the induced drag, which is pointing in the horizontal direction, in the direction of the rotation, in the plane of rotation, which I call delta fx, is density times the vertical component of velocity, which is the climb velocity capital V, plus induced velocity lowercase v, times gamma. So this is the Kutta-Joukowski theorem. Therefore, the lift can be related to the circulation. And circulation, of course, depends on the lift produced by the airfoil, specifically the angle of attack, which depends on the induced velocity, as we saw earlier. Now, what are the brown vortices? You look at a simple blade, okay, and the origin is at the axis of the rotation. So the vertical axis is the shaft axis. This is the axis about which the blade is rotating. The blade does not start at r equal to 0. It starts slightly outboard region, some 10%, 5% away from the 10% of the radius. So that region between 0% and 10% is called the cutout. Okay. So let me see if I can view my marker so that I could kind of move my marker for you. So I'm going to try to pick a color and a pen. So this line here is the blade. And then you have a cutout here, and this is the blade tip. So all along the blade, there is a bound circulation that is coming from root to tip. Okay, so let me see if I can go to the full screen and still see my marker. Probably not. So this is the bound circulation all along from root to tip. Bound circulation is all the vorticity contained in the boundary layer. At each radial location you have an airfoil. There's a vorticity on the upper surface boundary layer, on the lower surface boundary layer. If you integrate vorticity times area, or if you compute the line integral of velocity ds, that's the bound circulation. So the bound circulation is steadily increasing this way. So there's a theorem called Helmholtz theorem, which says if the circulation is increasing, we must be adding new circulation. So in this case, there's a vortex line that is coming from the far wake, way back here towards the blade, is bringing in the circulation. So same way here, this is bringing in the circulation, this is bringing in the circulation. These lines are called trailing vortices. Okay, these are the inboard vortices. There are infinite number of them. Each one is very, very weak because this is a continuously growing circulation. Therefore, a large number of very, very weak vortices are feeding circulation into the blade. So you see what you call a vortex sheet. You can visually see it when you visualize it in modern visualization techniques. So what happens at the tip is all the circulation drops to 0, because according to the Kutta-Joukowski theorem, which we saw in our previous slide, let me see, in my previous slide up here, not working. Let me turn the page up. not working. So in my previous slide, okay, density times velocity times circulation. So lift is increasing, but right at the tip, the lift should go to 0. That means what happened to all the circulation that is building up? It needs to be dumped into the wake as a very, very strong vortex. Okay. So this is the image of the bound. This is the bound vortexes all the way along the blade. This is the circulation in the boundary layer. Think of it that way. Trailing vortices are this weak vortex sheet that we see in the inboard region, and the tip vortex that we see right near the tip. Dynamic pressure is increasing as omega r squared. So if you look at the sense of these vortices, some would be clockwise, okay, as they approach the vortex. Think of it as a screwdriver. They are spinning in the clockwise direction as you approach from the far downstream boundary towards the blade. On the other hand, in the tip, notice that it's got an opposite rotation. That means it's leaving the blade and moving downwards. So think of it as a right-hand screw rule. Which way would the screwdriver rotate? Which way would the screw advance? So that gives you the sense of the vortex direction. So this is called the trailing vortices, or what's in the wake structure. Bound vortex is what's happening on the blade itself. Obviously, they are interconnected with each other. So this is the classical picture that Dr. Robin Gray came up with from his smoke visualization. It was not easy. He had a large Howard chamber. So he would introduce the smoke particles near the blade tip. Then he will darken the room. Then use a flash photography to light the region close to the blade and take a picture. So multiple snapshots, try to see what's going on. So he saw the tip vortex structure, which is shown as a black line, solid black line. And notice that it looks like a spiral shape. That means it's descending because the induced velocity pushes everything down, including the tip vortex structure. And you also see the inboard vortex sheet. One thing we notice that is that the inner vortex sheet seems to descend much more rapidly. Near the root, it descends slowly. Near the tip, it descends much more rapidly. So the inner vortex sheet detaches itself from the tip vortex, which is descending slightly slowly. And as the tip vortex descends, that means it's going from the rotor disc down into the far wake downwards. Not only it goes downwards, but it's also contracting. Okay, that means it's shrinking in radius. So Robin Gray was able to take a picture of all of these things, and he was able to come up with a curve fit for the descent rate. That means the rate at which the tip vortex is descending from the rotor disc. As a function of the blade location, think of it as azimuthal location. Azimuth 0 is behind the pilot, let's say. 360 is 1 full revolution. 720 degrees is 2 full revolutions, and so forth. So he came up with a curve fit, both for the descent ratio and also the contraction, how it is contracting. So he came up with a curve fit. So this is called a prescribed wake model. So he did this in 1952. Later on in the 1970s, Jack Landgrebe and Alan Egolf extended it to more general cases, not only for rotors in hover, but also for rotors in forward flight. So how did Landgrebe curve fit? He said, okay, if you look at a tip vortex, initially the rotor disc has got a disc area A. We know from our momentum theory, the induced velocity at the rotor disc is V. In the far wake, very far away, the induced velocity is 2 times V. Because density times area times the velocity is the mass flow rate inside this tube. So if the velocity is 2V, the disk at the right in the far downstream should be 1/2 of the rotor disk. That means the radius should be square root of pi r squared in the far wake divided by pi r squared in the rotor disk. it should be 1 over square root of 2. So the tip vortex radius in the far away case roughly 1 over square root of 2 times r. So this is a first guess at what should be the far field vortex location very far away from the rotor disk. The rotor disk is at psi equal to 0. Very large wake age. Think of it as a wake age as the age of a vortex after it leaves the blade. When it leaves the blade, its age is 0. Just as when a child is born from a mother's womb, its age is 0. Then every revolution, that means every year, the age increases. In this case, the vortex age is increasing from 0 to 2 pi, 4 pi, 6 pi, 2n pi. Every revolution is steadily increasing. Now, the curve fit that Jack Landgrave came up with and also Robin Gray was, rather than 0.707, they approximated this as 0.78 because the experimental data showed a slightly higher value for the tip vortex radius in the far away. This is the curve fit. So you non-dimensionalize the vortex age or radial location r of the vortex by the blade radius r. So you try to get a non-dimensional curve fit as much as possible so that it applies to a broad range of rotors, small rotors, large rotors. So it's got a fixed constant a plus 1 minus a times exponential of minus lambda times the vortex age in radians. So the vortex age in radians is, 2 pi will be 1 full revolution, 4 pi is 2 full revolutions, and so forth. Now lambda is an empirical curve fit in terms of 0.145 plus 27 times the thrust coefficient. Now we have a catch-22. If you don't know the thrust coefficient, you don't know the wake vortex structure. If you don't know the wake vortex structure, you don't know the inflow velocity, you cannot compute the thrust coefficient. So again, an iterative process is needed. We will describe it later. So what happens when this vortex age is 0, psi v equal to 0? E power minus lambda times psi v is 1. Therefore, a plus 1 minus a is just 1. Therefore, the tip vortex, r vortex, equal to r, right at the blade. So when the vortex age is 0, the vortex is emanating from the blade tip. What happens when the vortex age is infinity, very far away? E power minus lambda times psi v would be e power minus infinity, which is 0. Then the r vortex age by r would be simply capital A, which is 0.78. So this 0.78 is related to this 0.707 as we saw up here. So this was the initial curve fit that Robin Gray came up with, and Jack Landgrave improved it. So there are some papers, references to their work. So how about the descent rate? Both of them observed, Robin Gray originally observed, that initially the descent is slow. That means the tip vortex descends slowly until the following blade passes by. So if it's a two-bladed rotor, from 0 to pi of the vortex age, the vortex will descend at one rate. Then after the second blade has passed by, it will descend much more rapidly. Same way if you have a four-bladed rotor, 2 pi over 4 is 90 degrees. So the first 90 degrees, the descent rate will be slow. From 90 degrees onwards, the descent rate will be higher. Regardless, each one could be described as a linear curve fit of the vortex age. So this is the curve fit that was developed. Again, this is based on Landgrave. So there are some empirical constants K1 and K2. These are functions of the thrust coefficient, solidity, and also the blade twist. So once you find the thrust coefficient solidity or assume a thrust coefficient from one of our earlier methods, such as the blade element theory or a blade element momentum theory, compute K1 and K2, then solve for the vortex age from 0 to 2 pi over b, where b is the number of blades. Use one curve fit. And above 2 pi over b, use the second curve fit. Then compute the tip vortex structure. Okay, you have computed tip vortex structure. Now what? What do you do with it? So, by the way, earlier curve fits were based on the circulation gamma. In fact, the peak circulation gamma peak rather than CT over sigma. Regardless, you have to know the circulation or the sectional lift to compute the thrust. And then you compute this thrust, you can solve for these constants. Then you can compute the vortex geometry. And once you find the vortex geometry, you can compute the induced velocity, not by blade element theory, which is a uniform inflow, not by the combined blade element theory, which is a curve fit, not a curve fit, empirical, it's a quadratic equation. So what you do is you use a numerical technique called a Biot-Savart law. Remember, our tip vortex is a continuously helically contracting helical structure. So you break it into piecewise straight lines. So think of it as a spring that is compressed as you in the radial direction as you go from there. So spring is a continuous circular helical structure. You assume it to be approximated by piecewise straight lines. So each piece is from 0 to 15 degrees is one straight line, vortex edge. 15 degrees to 30 degrees is another one, and so forth. The tip vortex is assumed to be the maximum bound circulation. How do you compute the bound circulation? Reverse engineer from the Kutta-Joukowski theorem. So if you know the lift, delta T, then you can solve for the gamma. So you pick the peak value of gamma, then you take a 80% or just 100% at gamma. This is the circulation. Now, it's got a small core. Inside a small core, basically core is like there's a region of very, very low velocity swimming fluid. So outside the core, everything is moving very, very fast. Okay, sometimes this is called a Rankine core. Otherwise, the induced velocity will become infinitely high at the core. Okay, so this is the picture of the tip vortex structure. It's shown in red. So we have broken it into several small straight line segments. So it goes for several revolutions. I have shown only the first 15, 30, 45, 60 degrees of the tip vortex. And what are the blue dots? These are the center of the blade elements, like we did in the combined blade element momentum theory. When you divide the blade into small segments, radial segments, you pick a control point at the center of each segment. This is the blue dots. That's where we are going to compute the induced velocity. So we know the XYZ positions of those blue dots. They are radially located. And we know the XYZ locations of the tip vortex is piecewise structure. So every break point, you know you have an XYZ. Join all of them, you get a complete tip vortex structure. Now we need to compute the induced velocity from this vortex at these blue dots. Remember, induced velocity is lowercase v. So rather than analytically prescribing it using a blade element theory or combined blade element theory, now we are going to compute the induced velocity using the vortex theory. So we use something called a Biot-Savart law. Biot-Savart law says, let's say one of those broken line segments, this is a red line, is a segment of the vortex to vortex structure. Blue is the point in the center of a blade element where we are trying to compute the control. That's our control point. That's where we want to compute the induced velocity, lowercase v. So connect the two tips of the straight line segment of the tip vortex segment by position vector r1 and r2 as shown here. Once you have it, then the induced velocity at that control point is given by this empirical relationship. This comes from a theorem called Biot-Savart law, which is derived in a classical textbook in aerodynamics. We are not going to derive it in our course. I mentioned the vortex core, it is in the denominator. Why is it added? Otherwise, in the case R1 approaches R2, that means if the line segment becomes very, very small in length, okay, then what would happen is in the denominator, R1 and R2 is a magnitude of R1 and R2. So R1 R2 squared minus R1 dot R2 squared will go to 0 when R1 approaches R2, or if either R1 or R2 goes to 0. Okay, either case. Okay. Then the denominator will go to 0. To avoid that, we add this vortex core term to keep the velocities finite. In the numerator, you have this expression. And the gamma is the tip vortex strength. Remember, it's the peak circulation gamma computed from the peak lift distribution L. So you know gamma, then you can find the induced velocity. So initially you will find loading using blade element momentum theory. So all over from root to tip, you will have the lift distribution. From Biot-Savart law, compute the circulation, then find the peak value of circulation. So that's what we use here. So this is just for one line segment. Add it up over all the line segments. Okay, so you'll have hundreds of segments because each one is 15-degree age. So if you have, let's say, 3 revolutions, then you'll have at least 36, you'll have 72 segments. 72 times 15 is 10,080. That's 3 full revolutions. So sum it up over all the elements. So this is the numerical approach. So you compute the inflow first using blade element momentum theory. Compute the radial distribution of CL, CD. Then compute from the CL the lift value, which we call delta T, thrust earlier. So once you know the delta T, then you solve for the circulation from root to tip. Find the peak value of the circulation, gamma. So that's what you're using in the Biot-Savart law that is given in here. So compute the induced velocity by summing up over all the filaments. So once you have a radial distribution of loads converted to circulation strength using Biot-Savart law, find the P circulation strength. This is the strength of the tip vortex. Assume a prescribed vortex trajectory, either the Robin-Grace model or more commonly Landgrave's model. Landgrave's model is an improved version 20 years later. So throw away your induced velocity from blade element momentum theory, use the newly computed induced velocity, compute the new alpha, new phi, theta minus phi is alpha, just like you did in your blade element momentum theory, compute the new alpha, new CL, new CD, new lift. Now we have a whole new set of lift distribution, whole new set of bound circulation distribution, whole new set of peak values. Now use this new value, throw away the old values, go back and iterate on Biot-Savart law calculation, a loading calculation, iterate until it converges. Sometimes you know CT, that means you're given a thrust setting. That means you need to iteratively adjust the pitch angle, theta, up or down. If theta increases, you produce more thrust. If theta decreases, you produce less thrust. This is what a pilot does or an autopilot does in the case of a UAV or in the case of a manned or human-powered helicopter. So you trim it. So trim will be often part of this analysis. So this is how a prescribed vortex model is constructed. There are lots of programs which will compute this very, very efficiently. You can't do it on a spreadsheet quite easily because there's a lot of calculations. But a simple MATLAB code or a Fortran program would easily do this. Okay. How about free wake models? In free wake model, what you do is you initially start with a prescribed wake model. Then at each time step, you compute the induced velocity at these interface points where the line segments break at 15 degree, 30 degree, and so forth. Then you move the vortex based on the velocity. Remember, the vortex flows with the particles. It carried by the fluid particle, vorticity is convected by the flow. So you move it inward or outward, up or down, velocity, induced velocity times delta t to a new position. compared to the previous induced velocity. So the change in induced velocity times delta t. Okay. So the tip vortex structure now will no longer be our prescribed vortex structure. It will follow somewhat of a different structure. Now recompute it. Recompute the vortex strength. Redo it. Then when you do it, the positions are updated every time step. So now you march in time. Every time step compute the new induced velocity, not only on the broader disk for loading purposes, but also on the vortex structure itself, and move the vortex structure by a small distance, induced velocity times delta t, where delta t is the delta psi by which the blade is rotated, divided by the angular velocity omega. Okay. If you do this, then you'll get a more complicated vortex structure like this. Okay. So this is a free wake rather than a prescribed wake. So free wake can be modeled both for rotors in hover, but also in forward flight. So in many cases, we have a wake-on-wake interaction. So the inflow gets very, very complicated. Sometimes you want to see what happens to the snow on the ground or the sand on the ground. How does the snow gets kicked up? The sand gets kicked up, causing what you call a whiteout or a brownout. You want to look at the flow field, the entire flow field. So you can use Biot-Savart law to compute the entire flow field, not just at the rotor disk, but even at off-rotor locations. So Biot-Savart law based calculations and also the free wake calculations are very, very common. So in the US industry, they use a government software. There is a software called RCAS available from the Army, freely available. Wayne Johnson has got a program called Camera 2, which has got a free wake trajectories. And university solvers such as UMark, developed by Professor Chopra at University of Maryland, and GT Hybrid, a CFD plus free wake model generated at Georgia Tech in my own group. We have a lot of analytical codes for free wake trajectory and free wake induced velocity calculations. But there are also commercial solvers from companies such as Continuum Dynamics, and there are universities in Europe, in Israel, and other places, Korea, China, Japan, where these are all being done. So there's a lot of information available on the calculation of induced velocity. Therefore, we have computed the vortex theory. We have shown you how to compute the induced velocity using the vortex theory. So this particular video will stop.